Dr. Tyner, you're on mute.
Okay, so we are ready to roll. Thank you for that. Appreciate it. Last time we finished up with our Laplace transforms, all the properties, and spent a significant amount of time looking at the inverse Laplace transform. And so we had some homework problems. We took a look at one of them yesterday. Wonder if anybody has any questions on any of the homework that you had an opportunity to look at, or maybe you did not have an opportunity to look at it yet. Okay, well, let's do this then. Let's surge forward and let's get ourselves into chapter 13, lucky chapter 13, which is deep in many ways. It's a chapter that has a lot of information. It's not necessarily a long chapter, there's a lot of information, but some really valuable information about some properties that are, quite frankly, the heart and soul of electrical engineering, including the system function, the convolution integral, the convolution integral in the frequency domain and in the time domain, and that relationship as well. So we're going to take a look at all of those things. So here's what we're going to do. We're going to take the approach that we took with phasors with regard to our phasor transform. And so we're going to look at our circuit elements in the S domain and what happens in the S domain. And we know that the S domains means it's in the frequency domain. And the approach that we'll take will be very similar to the approach that we took. That was weird. The approach that we took when we were looking at the phasors, and we had each of the elements in our phasors. How do we transform a resistor? How do we transform an inductor? How do we transform a capacitor? So we're going to look at that here, and we're going to take a look at the resistor, the capacitor, and the inductor, and how do we do the transformation in the Laplace world. So those transforms are pretty interesting, and we're going to see why they're interesting. So let's start with the obvious and the easy one, the resistor. So we all know what a resistor looks like in our schematic diagram. There's the current I, there's the voltage V, and I know all of you know that it's a current I of T and a voltage V of T. We just tend not to put that in there. Our shorthand notation is we just leave the function of T out because we know everything is a function of T. So we don't bother to write it in there. We know the relationship is the following. V is equal to I times R. Just to be clear, I want to make sure everybody knows V of T is equal to I of T times R. There are a lot of reasons that we drop the of T and putting that T in there, and we'll see that with the frequency domain and the S and how we can confuse ourselves sometimes if we leave the function of S in there. We just tend not to do that, although many textbooks leave it in. So here's what I'm going to do. I'm going to Laplace both sides of this equation. Here, now that I'm taking a Laplace transform, I will be very clear that it is V of T. So the Laplace transform of V of T, that's pretty simple. That's V of S. And it's equal to the Laplace transform of I of T times R. R is a constant. So we can always pull the constant out in front of the Laplace transform. And we're left with the Laplace transform of I of T, but that's nothing more than I of S. So we have this relationship, V of S equals R times I of S, or capital V equals R times I. Notice I don't have a bar over the top of them this time, so no bar here, no bar here. So that means they're not phasors. They They're not phasors. The problem with this is when you look at it, you don't know if V and I are DC values. And that's why most authors of your textbooks do this right here. So they leave it with the function of S to be very clear. So there's no confusion. We're not talking about DC terms here. No confusion about that. Okay, so let's do this. Let's define Z sub R of S. And we're going to define that as the impedance. It's not just any old impedance, it's the impedance of a resistor. And so Z sub R of S is defined to be equal to V of S over I of S. Obviously, this is R for a resistor, given that the initial conditions are equal to 0. But there are no initial conditions for a resistor. We don't have to worry about it. So here we go, V of S. Well, V of S is R times I of S. And just like when we take the phasor transform, we convert a resistor in phasor world to be R ohms. We have the same thing here. So ZR of S, the impedance of a resistor is equal to R. So that means the following. When we transform this circuit element in the time domain, it looks like what we had up above. R, I, voltage V across it. And now in the frequency domain, we have I of S, R, V of S. So when we transform this resistor from the time domain to the frequency domain, the transform is simply just copy it over. Right? The Laplace transform of a resistor is just the resistor itself. So when we Laplace the resistor, that's trivial. There's nothing hard to do there. It's all done for us. Let's take a look at the capacitor and the inductor. So we'll start with the inductor. So we know for the inductor in the time domain, we always start in the time domain. There's our inductor L, there's a current I, there's a voltage V. And the current voltage relationship for any inductor is V is equal to L di dt. So we know that. So now what we're going to do for this one is we're going to take the Laplace transform of both sides of the equation. So the Laplace transform of V of t equals the Laplace transform of L times di dt. So left-hand side, pretty simple. V of S equals right-hand side. L is a constant. I can pull that out in front of the Laplace transform. It's just a multiplier. And then I have the Laplace transform of di dt. Now we can resort back to our properties. Our properties, when I take a derivative of a function, so let's see if we can recall up here. If f of t transforms into f of s, then f prime of t transforms into f of s minus f at 0. And of course, lots of textbooks use f at 0 minus for the case when there are switches in the circuit or in the network. Okay, well, right now we're not dealing with any switches in our circuit. So the Laplace transform of dIdt is S times I of S minus I of 0. This is equal to Ls I of S minus L I of 0. So that's what V of S is equal to. Okay, so this one's a little bit trickier. It's not so obvious. So first, let's go to the Laplace transform of just the inductor. So if I have an inductor and I want to transform it, what happens? Well, I have this L part here and I have this L part here. That's really interesting. If I wanted to declare an impedance, I'd follow the same description before. So it's defined to be the V of S divided by the I of S, provided initial conditions are equal to 0. Well, the initial condition is this term right there. If we set that equal to 0, then V of S is Ls I of S minus 0, so nothing there, divided by I of S. I of S cancels, and that's equal to Ls. So the impedance of an inductor is equal to Ls. Z sub L is just equal to, let's put the of S in there and make it clear. The L of S is equal to Ls. So anytime you are Laplace transforming an inductor, if there are no initial conditions, then we just replace it with Ls. I want you to note if we had Z, the impedance for the frequency domain when we were using phasors before, this is what we had before, Z was equal to j omega L. That's what we had before. This was for phasors. Over here, this is for anything. And notice, in the world of phasors, S is replaced by j omega. So there's something in the world of phasors that S is equal to j omega. And I think we know what it is. It has to do with that, the frequency of the sinusoid and how that's related to the Laplace transform. Here's what I really want to do, though. I want to look at what is the schematic equivalent of the inductor in the frequency domain. All right, well, let's rewrite this equation. V of S equals Ls I of S. V of S equals Ls I of S minus L I of 0. So I want to start with that one. And over here, I want to also solve for I of S. So see if you agree with this. So V of S plus L I of 0 equals Ls I of S. And then solving for I of S, we have I of S is equal to 1 over Ls V of S, and then plus Li at 0 gets divided by Ls, and that gives me I at 0 over S. So this is from the current perspective. This is from the voltage perspective. All right. Let's see what that looks like if I were to try to draw this. From a voltage perspective, it looks like the following. So from here to here was V of S. and this was I of S. Just following the direction that we had way back in this original picture. There's the direction of the current. There's the direction of the voltage. I selected the same direction. I have to. V of S and I of S are Laplace transforms of those. Now, if we look at this, what we see is the following. We see that this term is the voltage that comes from the current if the current were to go through an LS ohm impedance. So this voltage right here is LS I of S. That's that little voltage. Then I still have minus L times I at 0. So this is a constant value. It is a constant value. I at 0 is constant, L is a constant. So that's a number. But there's a negative sign, which tells me that the direction of this is opposite of this direction. So this one goes plus to minus, this one must go minus to plus. So this is one circuit model that we use when we have an inductor and we Laplace transform it when there are initial conditions. I want to remind you, this is the inductor. All of it. It's the initial condition and the inductance. Both of them. Of the inductor. And so I have I of S. Notice I of S is going into the big box, the inductor, and V of S is the voltage across the big inductor. So that's one way to look at this. All of you know that we can do a source transformation. This is a voltage source in series with an impedance, and I can transform that into a current source in parallel. But that's exactly what this does. This gives us the current source in parallel. So let's see if we can figure out what that one looks like. So I of S comes in, and it splits up into two terms. The total current is this term here, plus this term here. Now, the two of them are currents. How do I know the currents? Current is equal to a current plus a current. So that's a current, and this is a current over here. Both of those are currents. Now, if we do the same thing from here to here is the same as from there to there, then from here to here, I have plus minus Vs across the whole thing. So this current right here is Vs over Ls, which makes this Ls. And we knew that from source transformation. So the current is the voltage divided by the impedance. This one down here on the bottom, this one is just this term here. That's the current term. And so this current is I of 0 over S. And what direction does that go in? We'll see the plus sign. Both currents go in the same direction. So that current goes in this direction. Let's pause on this for a moment and talk about a couple things. So there are a couple of things I like to think of when I'm thinking of these initial conditions and what happens with the initial conditions for an inductor and for a capacitor, and what direction do we have these sources. And the directions of the sources, what I want you to think of, the direction of the sources, think of them as being dependent upon what the initial condition is. So the initial condition in an inductor is the current going through the inductor. So notice how the current going through the inductor is in this direction right here, and this source right here wants to keep the current going in that direction. This source wants to push a current in that direction. The minus to plus wants to push the current out the plus side. So that's how I remember how to put those voltage sources in. Generally, I don't like to put in current sources when I'm doing these conversions. I don't like to put in current sources. I like voltage sources. Why do I like voltage sources? Usually voltage sources, when you put them in the circuit, they result in one fewer equation. So I like to do that. So just as a reminder down here for this one, this is the inductor. The voltage is across the inductor. This is the current I of S that goes into the inductor right there. That's the current into the inductor. That's the voltage across the inductor. And this in the blue box is the model, that is the circuit model for an inductor. Okay? So when we're transforming the circuit, we know that if there are no initial conditions, LS is the impedance. If there are initial conditions, we have to include the impedance, plus we have to include the source, whether it's a current source or a voltage source. We always get to choose whether it's a current source or a voltage source. Always get to choose that. All right, the capacitor, we do the same exact thing with the capacitor, so let's do that. Capacitor looks just like the inductor, except we have the difference between where the derivative is. So 3 is for our capacitor. So we know I equals C VDT. So when we Laplace transform both sides of this equation, we get Laplace transform of I, or I of t, is equal to Laplace transform of C dV of t dt. And I know that you can look at this and say, gosh, that looks just like this equation up here that we had for the inductor. It looks like this one right here. And that equation, the only difference is V is on the left-hand side, I is on the right-hand side. This time there's flipped around. This time I is on the left-hand side, V is on the right-hand side. What the heck? Let's go through it again. It'll be good practice just to review this work. So this is I of S, and I of S is going to be equal to C times SV of S minus V at 0. Expand that. CS V of S minus C V at 0. So let's go ahead and rewrite that. So this is my I of S is equal to CS V of S minus C V at 0. Again, constant, impedance, voltage, current. Let's take that and solve for V of S. I think you can see that V of S is going to be equal to, I'm going to bring this over to this side of the equation and divide by CS. So it's going to be 1 over CS I of S. And then we're going to have plus, and we'll bring that over to the other side. Keep in mind we're dividing by CS plus V at 0 divided by S. Okay, so let's see what, we'll start with this one. We'll look at this one. We'll try to draw the model. This is in terms of voltages. So voltage, 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 voltage. I sum two voltages and they're equal to a voltage. Well, let's see. What does this one look like? Well, they're voltages and they add, so that's putting voltages in series. So it's going to be a voltage source. The overall voltage is here, plus minus V of S, from there to there. And that's equal to these two smaller voltages. So this tells me this impedance is 1 over CS. This is my I of S. So I goes into the positive terminal of this voltage. So that gives me a voltage there to there. That voltage is this quantity right here. So that is a positive. This is also a positive. So that must go like this. And that value is V of 0 over S. So when we're converting this, when we include the initial condition, we have to convert this is the capacitor. That is the capacitor. Obviously, it includes its initial conditions. If I use this either source transformation or use this equation over here on this side, using this equation for the I, what we have is this, the current source, okay? Obviously, the capacitor value is 1 over CS. The voltage across from here to here is V of S. So the current is the voltage divided by the impedance, V of S, divided by 1 over CS, that's CSVS, and then minus, so that current is going that direction. Minus means this current is going in this direction. Interesting. And that current value is C times V of 0. And this is the current I of S. I of S is each of those. Again, this is the capacitor. So these are models for the capacitor. These are models for the inductor. And the model for the resistor is just the trivial resistance. Boom, right there. So we have all three of our models in which we can work with to be able to do a transformation of our circuit into the frequency domain. I want to pause on these models for a moment, and I want you to understand, just looking at this. So the last time we looked at the inductor, now look at the capacitor. Look at what this source does right here for the capacitor. It wants to push a voltage in the plus minus direction. That's what it does, which wants to push current backwards. Think about why. If this is the voltage across the capacitor, then the condition of the voltage of the capacitor wants to push current this way. You store a voltage on it, but then when you take that voltage off of the circuit or out of the circuit, it's going to want to push current backwards from the direction that the voltage was applied. So it makes sense that that is the direction of the voltage source. Here's what I really want to look at. Look at this. V of 0 over S. If you inverse Laplace transform that, what does that look like in the time domain?
V0 U of t.
It looks like a unit step function. Now, it's a unit step function, but that step function is not going to hang around forever because it's immediately going to go through this here. And that's why it doesn't hang around forever. What does this look like in the time domain? An impulse function. An impulse of energy, a finite amount of energy in zero time that ends up dissipating through the circuit. That's what happens. So I don't want you to lose any sleep thinking too much about that, but it is interesting to note that. Now, given that we have all this information, Did we write that last impedance? I don't think we wrote that last impedance. Let's just go back up here, get that last impedance. Did we do that? We didn't. Z sub C of S is equal to V of S over I of S with initial conditions equal to 0, and that is going to be equal to V of S divided by, here's my I of S here with the initial condition 0. It's just going to be CS V of S, cancel, cancel, Z C of S equals 1 over CS. 1 over j omega C. S equals j omega. 1 over j omega C. It's the same thing. S is j omega. So we have all three impedances. So given that we know those impedances, what we can then focus on is we can focus on circuit analysis methods. So I'm not going to spend a lot of time on this, but this is what I want to show you. So basically, this is what we have. Everything that we've used before still applies in the Laplace world. What do I mean? KCL, KVL, Ohm's law. Ohm's law is just not done with resistors, it's done with impedances. Series, parallel. Okay, so combinations in series and in parallel. Thevenin and Norton. Source transformation. Mesh and nodal analysis. Etc. Right? Superposition, linearity. All of those still hold. I just want to quickly prove to you one of them. I'm just going to prove KCL. Okay, in the time domain, we have the following. The sum of the i's are equal to 0. Let's call this K. The sum from K equals 1 to N, however many of them there are. In other words, I1 plus I2 plus I3 sum them up, they're all equal to 0. Same thing would be true for the voltages. Sum up all the voltages, they're equal to 0 in a loop. So that's Kirchhoff's current law, Kirchhoff's voltage law. Okay, well, let's Laplace both sides. We know that this first term can be broken up as the sum of Laplace transforms. And I know everybody knows that the Laplace transform of 0 is 0. Laplace transform of I1 of S, plus I2 of S, plus I3 of S, plus IN of S equals 0. Proof, QED, done. Sum of the currents is equal to 0. Doesn't matter whether you do it in the time domain or if you do it in the frequency domain. It does not matter. So I'm not going to spend a whole bunch of time going over all of those and proving to you that they all hold in the frequency domain. I just want you to know they all hold in the frequency domain. So now let's talk about what the steps are going to be for solving our circuit problems. So I want you to note the following. So number one, if the sources are just sinusoidal and or DC, use the circuit analysis techniques that we already know. So don't use Laplace. Use the circuit techniques already discussed this semester. So that's DC analysis or phasor analysis. Okay, so if you see a circuit that just has DC inputs or just has sinusoidal inputs, don't waste your time doing Laplace. These techniques, as we've seen, get more and more sophisticated. So they're harder, not easier. So we're using them because they solve problems for us faster than using differential equations. But if we have a DC case or an AC case where there's sinusoidal inputs, we've already come up with tools that allow us to solve those problems. Otherwise, transform the circuit into the S domain. S domain is the frequency domain. A lot of interchangeable terminology that I use. How do we do that? A, resistors, go to resistors. B, inductors, go to LS. C, capacitors, 1 over CS. Let me tell you what stinks here about capacitors. That was really nice when we had sinusoidal steady state. 1 over CS is always 1 over CS. You can't take the S out of the denominator and change it to a minus S in the numerator, like we could with J's. We can't do that, unfortunately. So we have to leave it there. So we do that. Then we form our sources. So sources. We take the Laplace transform. Okay, so we're gonna do that. All of our currents and voltages are going to be labeled different. I, V, I'm sorry, lowercase v, go to, and this is going to be your preference. I'm going to recommend you stay away from it and do the following: capital I, capital V, or I'll write it this way: I of S, V of S. I like this. I love this. I'd rather do that, but I have found that people confuse this right here with looking like it multiplies by S, which we do a lot of in the frequency domain. And so it confuses them. So when I do the analysis, I usually do this. Then when I put answers in, I usually do this. So when we transform the circuit, we're going to do all of that. Now, here, for these two, I'm just going to remind you that we might also need to also include the initial conditions. So that transformation might not just be, it goes to LS, you might have to put the LS part in, and then you might have to put the initial conditions in also. A lot of our circuits are not going to have initial conditions. Woohoo! Thank goodness. It's going to save us a lot of time. But several will, and you have to know how to handle that. So we want to make sure we do all that properly. Okay, so we've done all of this conversion in the circuit. And step 3 is we're going to perform circuit analysis. So when we do that circuit analysis, solve for the desired Laplace transform function or functions. What do I mean? Like maybe I want V1 of S, right? This would be, for example, what function are you after? So you solve for that desired function. Once you have it, you are probably going to have to do the following. Perform the partial fraction expansion. Once you've done the partial fraction expansion, then you're going to convert back to the time domain. That would be, in this case, in this example, V1 or V1 of t. Convert back to the time domain by obviously inverse Laplace, but where those inverse Laplace coming from, I'm going to call it by lookup table. In knowledge of properties. So it's not like every single one of them is in the table. You have to know your properties too. Then once you've done that, solve the problem. I don't know what the problem is, but solve or answer the question, right? That's what I mean when I say solve the problem. Answer the question. Or find what you were asked to find. So that's the process that we're going to use to solve our problems. Let's look at a couple of examples to get us going. Let's start by just finding an impedance. Find the equivalent impedance and admittance. Let's do both of them. And we're going to do this to the right of terminals AB. All right, here's what we have. Inductor, 2 Henrys. A 1/4 farad capacitor, another inductor, 1 Henry, another capacitor, 1/2 farad. So here's A and B. And we're looking for this impedance looking in here. Z of S. And we know that Y of S is just 1 over Z of S. That doesn't change. Everything's the same. Okay, I think we can do this with series parallel combinations. Everybody agree with that? Probably the easiest way to do it, series parallel combinations. So those two are in series. And then that'll be in parallel with that. And then that'll be in series with this last one. So the first thing we have to do, transform the circuit. 4 over S, 2 over S, S, 2S. I'm just using LS and 1 over CS. Okay, so this first one in series, let's call this Z1. Z1 equals S plus 2 over S. I'm not sure right now whether or not that's the form I want it in. We could figure out, we don't have to figure it out, but one of the things that we're going to recognize pretty quickly is that notice we can't just get rid of the S in the denominator. We can't get rid of it because there's only one side to this equation. Usually we get rid of denominators by multiplying both sides of the equation by the common denominator, and one side of that equation has the number 0. So 0 times anything is 0. There's only one side to this equation that has a term, and that's it right there. That's Z1. So this is going to be equal to common denominator is S. So it's going to be S times S plus 2, which is S squared plus 2 over S. That's Z1. Let's let all of this be Z2. So it's going to be Z1 in parallel with 4 over S. So that's the product over the sums. S squared plus 2 over S times 4 over S, product over the sum. S squared plus 2 over S plus 4 over S. That's nice in the denominator. So in the numerator, I have 4 times S squared plus 2 divided by S squared, all divided by S squared plus 6 over S. And you just flip that around, and that's going to be equal to 4 S squared plus 2 divided by S squared times S over S squared plus 6. So if I didn't make any mistakes, 4 times S squared plus 2 over S squared plus 6. Hopefully I didn't make any mistakes there. Okay, now the total Z is...
Isn't the denominator S times S squared plus 6?
You gotta help me. Here...
No, just
gotta get. I see. It's. Is that what you said?
Yeah.
That's correct because only one of these cancels. You're right. I put a line through the 2 and it looked like the line was through the S. You're correct. Thanks, Jack. Beautiful. Okay. So now our Z equivalent is equal to 2S plus this mess, which was Z2. So that's equal to, did I call it just Z2? I just called it Z2. So let's stick with Z2, not Z2 of S. Okay, so that's equal to 2S plus 4 S squared plus 2 divided by S squared plus 6. Equals common denominator. This gets a little ugly. So 2S times S times S squared plus 6 plus 4 times S squared plus 2, all divided by S times S squared plus 6. Now it's just grind through it. Grind through this. So all of this is equal to 2 times S times S times S squared, 2S to the 4th, plus 12 S squared, plus 4S squared, plus 2, all divided by S times S squared plus 6, which is equal to 2S to the 4th, plus 12, 16, S squared, plus 2, over S squared plus 6. So that's just an example of using using the series parallel combinations in the Laplace domain. We can do that. Put my units on that, my units are ohms. If we're looking for y of s equals 1 over z of s, that's equal to this whole fraction flipped. It's going to be s squared plus 6 divided by 2s to the 4th power plus 16 s squared plus 2, and that would be in Siemens. So we can utilize those same tools that we had before, no problem, still works out. It's fairly similar to what we had. It's just we have s's in there instead of j's. Our s is a little bit harder to work with. Depends if you like complex numbers or if you don't like complex numbers. Okay, let's do this example. Let's find the Thevenin equivalent in the frequency domain to the left of AD if V at 0 equals 0, I at 0 equals 0. Okay, so let's take a look at what this circuit looks like. So this circuit, we have source, 5 sine of 2t. Capacitor. The capacitor is a 1 farad capacitor. And then over here, we have an inductor, 2 henries, and a resistor, 4 ohms. A, B. Now, even though this is a sinusoid here, we could do this all in sinusoidal analysis. That was V, this was I. Obviously, we won't want the initial conditions, voltage across capacitor, current through the inductor. But I want to tackle this in the Laplace world. Even though I said, hey, we've already got these techniques, let's tackle this in the Laplace world. So let's start by one of 2 different techniques. We can find the impedance first, we can find the voltage, the open circuit voltage, short circuit current. All of those techniques still apply. So let's do this. Let's start by, let's find Z Thevenin. So we haven't done this in a while. Do you remember how we find the Z Thevenin? Anybody remember how we do that?
We take out the source and combine the impedances.
Excellent. Take out the source, kill the source, combine the impedances. So I'm going to kill that source. There it is. Then I'm just left with this capacitor. So 1 farad capacitor. And I have this inductor. And I have this resistor. A, B, 4, 2. All right. Now I'm going to convert. 1 over S, love that. 2S, 4 stays 4. We're looking for the impedance looking in here. Z Thev. Well, Z Thev equals 1 over S in parallel with 2S plus 4. Equals 1 over S in parallel with 2 times S plus 2. Just try to reduce things whenever we can. That's product of the sums. Equals 1 over S times 2 times S plus 2 divided by 1 over S plus twice S plus 2. Multiply by S over S. It's a great way to get rid of those S's in the denominator. So when I do that, in the numerator I have 2 times S plus 2, and in the denominator I have 1 plus 2S S plus 2. Let's get the whole thing here. This whole impedance is, that's equal to 2 times S plus 2. And then I have 2S squared plus 4S plus 1. 2S squared plus 4S plus 1. Everybody like that? That look good? Okay, that's half the problem done. That's the Thevenin equivalent. Now, when I go back to this circuit, we see our circuit up here. I can either find this, the open circuit voltage, obviously we want it in the frequency domain, so I can find that, or I can put a short there and find the short circuit current. So I can put a short here and find the short circuit current. I'm not sure which one's easier. So you tell me which one you want to do, the open circuit voltage or the short circuit current. They both seem fairly easy. No preference? You're sleeping? Let's find VOC. Okay, so we've got to get that circuit. So let's draw that circuit and convert it. Make sure we have the same circuit again. So there's my A, there's my B, lowercase VOC, source, capacitor, inductor, resistor. Resistor is 4 ohms. That was 2. That was 1. And then the source that we had was 5 cosine of 2t. Is that correct? Did I not label that source? I did, right? Yep.
I think it was 5 sine.
5 sine. 5 sine 2t. Okay, so convert the circuit. We've been having a grand old time converting circuits. So let's go ahead and convert that circuit. 1 over S, 2S, 4, 5 sine of 2t. 5 times 2, 10, divided by S squared plus 2 squared. S squared plus 4. VOC over here. Okay. Well, this is just a single loop circuit. That's the current I. And so we know I is equal to the voltage, which is 10 divided by S squared plus 4, all divided by 2S plus 4 plus 1 over S. Let's get that 1 over S out of the denominator. So this is going to be 10S over S squared plus 4 divided by 2S squared plus 4S plus 1. So I is equal to 10S divided by S squared plus 4 times 2S squared plus 4S plus 1. In this world, generally, you love to leave things with as factors. Don't multiply them together. Leave them as factors. Okay, that's the current. Notice back in this picture, the voltage from here to here is the voltage here across the source in this, and it's also the voltage from here to there. So it's nothing more than the voltage across the inductor and the resistor. And I'm going to use that because that voltage is I of S times 2S plus 4. Okay, that's equal to 10S divided by S squared plus 4, 2S squared plus 4S plus 1. That's I times 2S plus 4. So that is simply equal to 10S. Actually, let's pull this 2 out. Okay, let's pull the 2 out and just double that, multiply there. That's 20. 20S, S plus 2, divided by S squared plus 4, 2S squared plus 4S plus 1. This is the reason that we don't multiply through these, especially in the denominator. The numerator you can multiply through if you want to. The denominator, don't do it. Because if we were doing partial fraction expansion, we'd have to get it back to these factors. So we have our impedance, we have our voltage. So here, there's the impedance, here's the voltage, A, B. Notice the plus minus, the plus is at the A terminal, the minus is at the B terminal, exactly the same as the original picture. This is 20S, S plus 2, divided by S squared plus 4, 2S squared plus 4S plus 1. And the impedance was, I'll pull that back to get the impedance, because I don't remember it. Right there, 2 times S plus 2, divided by 2 squared plus 4S plus 1. And there's our Thevenin equivalent. That's in the frequency domain. It is not the Thevenin equivalent in the time domain. Any idea what would happen with this in the time domain? What would happen there and why it happens? Well, you'd have to do partial fraction expansion. We're going to get terms from that denominator. Everybody agree the terms we get from that denominator is going to be the sinusoid? So that's the forced response. Then from this, we're going to get 2 more terms, and those are going to be the natural response. Those are going to be exponentials. So we're leaving it in the frequency domain. We don't care about looking at it in the time domain. We'll have reason to do that at some other time. Let's take ourselves a 5-minute break. We'll come back in 5 minutes, and then we'll start up and we'll look at one more example, and then we'll continue forward with some analysis of 1 or 2 more examples, maybe a little bit more than that. And then we'll start just going through different things that we can do in terms of our frequency domain analysis. A lot of this, I just want to do a lot of these examples because these problems are much harder to work and to solve than the standard problems that we've had. I think these are more difficult than solving with complex numbers using phasors. That's my personal opinion, because we're solving functions with fractions, and there are a lot of pieces to the puzzle when we do that. So why don't we go ahead and take a 5-minute break? We'll come back in 5 minutes and we'll pick up our recording. Okay, any questions on what we've done? Who can summarize? I know we did some examples there. We spent a little bit of time doing examples. Who can summarize what we just learned? Well, what's your takeaway from what we just covered?
that our circuit analysis steps are pretty similar to what we did with phasors, with the exception that the conversions were different for the impedances.
Excellent. Okay, that was one piece. There was another piece to that, Jack. If you can nail it, there's one more piece, and it's really the part of the power of Laplace analysis. There are several things that are powerful about it, but in that conversion, there's one other thing that's different.
Is it the sources?
Nope. It's the storage elements. What can it do with the storage elements? Even though we didn't do it in any example yet. We can convert the storage element and the information about its initial condition. So that's really what we've added on here. So all that we've done before, gosh, we did another Thevenin equivalent. Oh my gosh, that was really exciting. And then we did another example of finding the impedance. Ooh, really exciting. But now the real power is what happens when we have energy stored in those devices. What do? How do we handle that? Because if we can't handle that, then all of this Laplace material just seems like an extension of what we've done before, except it can handle different sources. That would be the difference to me. It can handle different sources. But that's not it. So let's go ahead and take a look and continue down the example lane of looking at circuit analysis using these methods. And let's take a look at what happens and what we get. So in this next example, I am going to give some initial conditions. So here's our circuit. Let's leave this as VG, voltage source. And then we have an inductor, a 1 Henry inductor, a 2 ohm resistor. Your author of this textbook loves this circuit. This is called, just so you get comfortable with this, because you're going to read about this and hear about this a lot. This is the series RLC circuit. So it's a resistor, capacitor, and inductor. They're in series. It's a cool circuit for a lot of reasons. We're going to learn a lot about this very simple series RLC circuit. So the author is focused on these kinds of circuits. I just want to make sure we see one. And so this will be V, and this will be I. And this is what we want to do. We're going to get the whole gamut here. Find I, and it's going to be for t greater than 0. Why? Because we don't know anything about t less than 0. Find I for t greater than 0 if V0, V at 0 is equal to 6. I of 0 is equal to 2. And if A, VG is equal to 10, and B, VG is equal to 4 cosine of t. Now, both of these, you're looking at it and you say, well, wait a minute, V of G is 10, that's a constant. We could do this with our old methods. Well, not with the initial conditions, you can't. VG is 4 cosine of t. We can do that with our old methods. Not with the initial conditions. You can't do that with initial conditions because phasors do not include initial conditions. All right, where do we start? Well, step 1 is convert the circuit. So to convert the circuit, I'm going to actually redraw the circuit because it's not as easy as just converting it. And the reason is because I'm going to take those initial conditions into consideration. What I'm going to do is I'm going to put the initial conditions in as voltage sources. Why? Why will I put them in as voltage sources? I want you to think about that for a moment. So in other words, if I put them in as current sources, I'll end up with something like this, right? The current source would be here. Over here, the current source would be there. If I put them in as current sources, they'll look like that. What happens if I put them in as voltage sources? What cool thing happens? If I put them in as voltage sources, they will be in series with the element. If they're in series, then I will still have one loop in my circuit. Okay, the inductor looks like an inductor and a source. A resistor looks like a resistor. A capacitor looks like a capacitor and a source. It doesn't matter whether you put the capacitor first or the source first. It doesn't matter if you put the inductor first or the source first. That doesn't matter. Let's do the easy things. V, if we were putting this V, I just want to remind you, it's there. That's the V. That would be the I. Okay, but we're in the frequency domain because this circuit is frequency domain. So let's get the time domain out of there. This is what I'm going to do. I am going to leave this as VG. I'm not going to do part A and then go back into the circuit for part B, and you're going to see why. So this is the smart approach, and this is going to lead us to our transfer function or our system function. So just call it VG. This one converts to 1S, which is just S. Now the question is, which way does the source go? It's going to want to continue to pump current in the same direction. So what is the value of that current? Do you remember? It's L times I at 0. So just as a reminder here, L times I at 0 is equal to, well, the value of L is 1, and I of 0, we said, is 2. So this is a source of value 2. That stays 2. This becomes 5 over S. And this voltage source goes in that way, which was the direction of V, the direction of V. And that voltage is, as a reminder, and I'll write that down the bottom, V of 0 over S. V of 0 over S is 6 over S. And there we have it. Now, there's circuit analysis right there. See if you agree. That's I, so that must be I. Let's put the of S in there later on. And that's what we're after. Find I for t greater than 0. I in the time domain, not I in the frequency domain. So we'll have to find I in the time domain after we find I in the frequency domain. Let's pull that down a little bit so we can see the entire circuit. Okay, here we go. Okay, I have 3 sources. So I think you can see that we don't actually have to write the KVL equation. We can if we want to around this loop. Well, we've got 3 voltage sources in series. We have 3 impedances in series. And so the total voltage that we're after, or the current, I'm sorry, not the voltage, the total current that I'm after, I, is nothing more than, I'll just write it this way, the sum of the voltages divided by the sum of the impedances. So let's see what that is. So I goes in this direction, so we want the voltages that are minus to plus are positive, and the ones that are plus to minus are negative. So in the numerator, I have VG plus 2 minus 6 over S. And for my impedances, I have S plus 2 plus 5 over S. I'm going to start to clean up. Get rid of those ugly denominators. So that's going to give me S squared plus 2S plus 5, not bad. In the numerator, SVG plus 2S minus 6. So that is what I is equal to. Now, let's work part A. Part A, VG is equal to what? Well, for A, let's start with this, maybe. Let's put little VG for part A. So for part A, we said that VG was equal to 10. We're only doing this for t greater than 0. So does everybody agree that I can write this? I want I for t greater than 0. So it's 10 u of t. Is that okay? For t greater than 0, that function is equal to 10. It's equal to 10 here. It's equal to 10 here. VG is 10 over S. All right, let's plug that in. So I equals S times 10 over S is 2S minus 6 S squared plus 2S plus 5. Today's our lucky day. So cancel, cancel. 2S minus 6 plus 10 plus 4 divided by S squared plus 2S plus 5. I've seen this denominator 6,000 times. I'm going to help you with it. 2S plus 4, S plus 1 squared plus 2 squared. Okay, that's I. That's not what we're asked for. We're asked for little I. So now we have to do the partial fraction expansion. So we have two choices of the partial fraction expansion. One is use the complex numbers and do it that way. Or two is recognize this thing is ready to go. It's ready to be expanded. There's only one complex term in the denominator. They're complex conjugates. So remember that this is so the first thing I need is I need an S plus 1. But how many S's do I have up here? How many S's are there?
2.
Good. How many S's are here in the numerator here? There's only one there. I need 2 of them. So I have that. So right now I have, just as a notation to keep track, this is 2S plus 2. But I want plus 4. So I need 2 more. And I was nice to you on this one because this is exactly what we need here. This is exactly what we need over here. So we are ready to inverse. So I of t is equal to, it's the inverse of this term, twice e to the minus t cosine of 2t plus this one is, this 2 needs to be there to match this 2 down here. That is just e to the minus t sine of 2t. And you're starting to recognize between yesterday's quiz and now today, you need to be pretty sharp on your feet and you need to quickly recognize these Laplace transforms, the inverses, and going forward, you need to recognize them very quickly. So yeah, you have a lookup table to look things up, but start learning some of these by doing your homework assignments and giving you an opportunity to be able to see those very quickly. So let's put my units in there. My unit is amps. It's a current, it's in amps. Notice something interesting. I'm noticing it. Maybe you didn't. So let's notice it together. Make sure we both notice it. The source in this particular function is what kind of a source? What kind of a source?
Constant source.
Constant source, DC source. It's a constant source. So do you see any constant terms in the output here? Anybody see any constant terms there? Just a constant. I don't. Why not?
No.
Back here, when this is DC, what does this inductor look like to DC?
Skip, 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 skip.
What does that inductor look like at DC? Connor, you're unmuted. At DC, this inductor looks like a short. This capacitor looks like an open. That puts an open right here. Flows through that loop. as far as this constant source. The constant source, zero current can flow through there. And that's why there is no constant term here. Let's go to B. Part B, we had VG was equal to, and I know it was a cosine, I believe. Let's scroll back here. Okay, 4 cosine of t. So VG is 4 cosine of t. So VG equals 4s over s squared plus 1 squared. Four s over s squared plus 1. Okay, so we'll use the same analysis approach that we just used. We have VG, we're just going to substitute VG into this equation right here for I. Not that, come on. Let's go back to where you were at. Beautiful. This equation for I right here. SVG plus 2 of S minus 6. So I equals SVG plus 2S minus 6. What just happened there? That was weird. I equals SVG plus 2 of S minus 6 divided by, and it looks like we had S squared plus 2S plus 5. Okay, so now we're going to substitute in our VG. That's equal to S times 4S over S squared plus 1. Boy, does that look ugly. Plus 2S minus 6. S squared plus 2S plus 5. And you're going to run into a lot of these. Over and over and over again, you're going to run into a lot of these functions that they just start to get ugly. You just deal with it. It's not a problem. All right, numerator first. So I have 4S squared plus 2S times S squared plus 1 minus 6 times S squared plus 1. So all I'm doing is I'm forming a common denominator in the numerator, all over S squared plus 1, and then all of that is all over S squared plus 2S plus 5. I think we know what's going to happen here in the denominator. We end up with S squared plus 1 times S squared plus 2S plus 5. We have that. And now, in the numerator, I have 2 times S squared, that's 2S cubed. So I took care of that term. 4S squared minus 6S squared minus 2S squared. And then I have plus 2S here with that one, plus 2S minus 6. That's our numerator. Okay, everybody like that? For that term, 4 squared minus 2S squared plus 2S minus 6. All right, now what do we have to do to find I? Partial fraction expansion, right? So A over S plus J plus A conjugate over S minus J plus B over S plus 1 minus 2J. Notice I always want the minus first, the negative. Always do that one first with your B term. Plus B conjugate S plus 1 plus 2J. All right, it's just All we have to do is solve for two of them. Solve for A, solve for B. That's the beauty here. We don't have to solve for all four of them because once we have two, we have the other two because of that complex conjugate property. That's sweet. Okay, so let's start solving for A. So A is equal to S plus J times I of S. Remember, this is the I function, not the F of S function that we're used to. Evaluated when S equals minus J. So that's equal to that ugly numerator. So it's 2 times S cubed minus 2S squared plus 2S minus 6 divided by S minus J. And then here, no need to break it out, just leave it S squared plus 2S plus 5. All evaluated when S equals minus J. That won't be too bad because minus J is not such a bad number. We can deal with that. Okay, let's see what that's equal to. So minus J cubed. What's minus J cubed? Two. Okay, let's write these. Let's plug them in so you can see what I'm doing. Minus J cubed minus 2 times minus J squared plus 2 times minus J minus 6 all divided by minus J minus J squared plus 2 times minus J plus 5 equals minus J times minus J. That's minus 1 times another minus J. That's plus J. 2J minus J squared minus 1 times 2 times 2 is minus 2 with a negative in front of it, plus 2 minus 2J minus 6 all divided by minus J minus 2J minus J squared negative 1 minus 2J plus 5. Not too bad. Equals. Just keep working with it. It's just mathematics. And that's equal to, you can see, cancel. And I have 2 minus 6. That's minus 4. I have minus 4 in the numerator. I did all my work correctly. And then minus 4 divided by minus 2J, and then 5 minus 1 is 4 minus 2J. Okay, I can factor a 2 out of that, so it's minus 4 over. Take that minus 2, J, and then another 2, and then 2 minus J. And so that whole minus 4 cancels with that. So this is equal to 1 over 1 plus 2J times 1 plus 2J over 1 plus 2J equals 1/5 times 1 plus 2J. It's not the form we wanted in. The form we wanted in is polar form. So here we go. So it's going to be root 5 over 5 at an angle tan inverse of the imaginary over the real. That is A. Save that, we need that. Now we need B. So, to solve for B, B is going to be, let's see if we can remember what we had there. We had the terms written out. So I'm multiplying through. So I'm going to have the S squared plus 1 in the denominator. Let's first get that numerator. 2S equals that. Gosh. Excuse me for a second. Put that to voicemail. Okay. B equals. So then it's going to be S plus 1 minus 2j times I of S evaluated when S equals minus 1 plus 2j. Remember, it's always the value of S that causes this whole term to be equal to 0. So it's negative these numbers there. Okay, so that's going to be equal to, let's go back to the function. So the function that we had was 2s cubed minus 2s squared plus 2s minus 6 divided by, now leave the s squared plus 1 alone. And then the other term over here is s plus 1 plus 2j. When s equals minus 1 plus 2j. All right, I don't think that's too bad to deal with. So let's start working with that one. So this is equal to, as I start substituting in, it's going to be 2 times minus 1 plus 2j cubed. Not the coolest. Minus 2 times minus 1 plus 2j squared plus 2 times minus 1 plus 2j minus 6, all divided by minus 1 plus 2j squared plus 1, and then this one's nice, minus 1 plus 2j plus 1 plus 2j. Okay, so we need to do a little work side. So right up here in this space, I'm going to minus 1 plus 2j times minus 1 plus 2j. That'll give me the square. So this is equal to, the real part, I get minus 1 times minus 1, that's positive 1. 2j times 2j is minus 4. 1 minus 4 is minus 3. And then I get the minus 1 times 2j, and then this minus 1 times that 2j, obviously, so it happens twice. We know that. So that's going to be a minus 2j, and a minus 2j is minus 4j. So that's minus 1 plus 2j squared. Minus 1 plus 2j squared is equal to minus 3 minus 4j. We're going to have to remember that when we plug that in. Okay, now I want it cubed. So to cube it, I take minus 3 minus 4j, and I multiply it by minus 1 plus 2j again. The real part, I get minus 3 times minus 1, that's positive 3, and then I have a minus 4j times a positive 2j, that's going to give me a positive 8. 8 plus 3. 8 plus 3 is 11. And then I have a plus 4j minus 6j, that's minus 2j. If I did that correctly, minus 2j. Anybody see any mistake with that? Does that look okay? 11 minus 2j. So this is minus 1 plus 2j cubed, and this is minus 1 plus 2j squared. So we'll substitute those in. Okay. So this mess is equal to twice minus 3. Come on, go away. Thank you. Minus 3 minus 4j minus 2 times, oops, sorry, first one's wrong. That's cubed. So if it's cubed, it's 11 minus 2j, 11 minus 2j. The second one is not cubed. The second one is squared. So it's minus 2 times minus 3 minus 4j plus 2 times minus 1 plus 2j minus 6, all divided by first one, minus 1 plus 2j squared minus 3 minus 4j plus 1 minus 1 plus 2j. We can just figure this last one out. We don't even need to write it. That's minus 1, plus 1, it's 4j. All right, now we've got all terms that are easy to figure out. So let's get the real part first. So I have 22, and then I have minus 2 times minus 3 plus 6. Then I have minus 2 and then minus 6. That's the real part. Let's get the j part. So the j part is minus 4 plus 8 plus 4. I don't know what happened here. Minus 4 plus 8 plus 4. Okay, let's cancel with each other there. In the bottom, I have this minus 3 plus that 1 is minus 2. I'm going to pull out that negative 2. And that's going to multiply 1 plus 2j times 4j, there's j times 4. So I can see those numbers easily and start multiplying them together and working through them. Okay, so notice, by the way, what we're doing is just a lot of manipulation with complex numbers. A lot of manipulation with complex numbers. Equals. And this is why a lot of people like to stay away from them. 22 minus 2, 20. Plus j8. I'm going to factor 4 out of that. And so leave that 4 there. And now I'm going to multiply these. When I do, I get j times this 2j is minus 2. With that minus 2 is minus 4, but I'm going to leave that minus 2 out there. So minus 2, and then plus j. And then leave this minus 2 here, so I can cancel with this 4. So when I cancel with this 4, I'm going to end up with 2, 5. So it's 5 plus 2j divided by, leave this negative 2 here right now, and then I have minus 2 plus j, minus 2 minus j, minus 2 minus j, equals minus 2. So we're going to end up with, when I multiply those two together, minus 2 squared, 4, 1 squared, plus 1, 5. Beautiful. Now in the numerator, the real part, minus 10 plus 2, 12. And then minus 4, minus 5 more, looks like. Okay, so all of this is equal to 12 minus 9j. Let's get the 9j. I'm going to factor 3 out right now. Okay. Got a frozen screen for a moment here. Just there we go. Okay, so I'm going to factor 3 out. 3 times 4 minus 3j divided by minus 2 times 5 divided by minus 10. Okay, I'm going to take this negative and I'm going to put it inside of the complex number, like this, because we don't want negative numbers as radial distances. So this is 3/10 times 3, 4, 5. It's a 5, 3, 4, 5 triangle. 5 at an angle of tan inverse of 3 over minus 4. So that's equal to 3/2 tan inverse 3 over minus 4. Beautiful. We have our two numbers. Whew, that was tough. So that's B. All right. So if we recall back in our partial fraction expansion, we had this. I was equal to A over S minus J plus da 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 plus B over S plus 1 minus 2j plus its term. So we've got B right here. This is B. And A is missing, so let's rewrite A. A, I have to pull back and see what I had for A. So just give me 1 second to pull this back. To get to A, there was B. Come on, a little bit more. Root 5 over 5, 10 inverse, 2 over 1. Root 5 over 5. A equals root 5 over 5, 10 inverse, 2 over 1. All right, so what happens when we inverse these two terms? If you remember, we're going to get the following. 5 over 5 times 2, it doubles. Cosine of, I look down here at the bottom, there's no real part, there's only an imaginary part, that's why there's no exponential. So I get this 1t, cosine of t, plus I get this phase shift over here from A. Tan inverse of 2 over 1. That's that term. From the second one, I get the same sort of thing. So I get this multiplied by 2, 3/2 times 2 times e to the minus 1t cosine of 2t, and then I have its angle, and its angle is plus tan inverse of 3 over minus 4. And that is I in amps. Boom, box it up. Obviously, you can multiply those numbers through. Those twos cancel. And that is our answer. And wasn't that ugly? And that's what you're going to find is every time we're dealing with functions like this, every time we're working in the frequency domain, what happens is our math just gets tougher and tougher. It's not difficult, meaning it's mathematics you've never seen before. I want to remind you, I always remind you, what's the hardest part about calculus? It's the algebra. What's the hardest part about circuit theory? It's the algebra. It's all the algebraic manipulations that we were doing. If these were trivial numbers, we could have whipped through this problem just like that. It would have been easy. You would have loved it, and it wouldn't have been any problem. But that's not the case. Unfortunately, the case here is what we have is we're dealing with functions. And when we're dealing with functions, there's a lot of additional work that needs to take place versus just dealing with numbers. But stick with it. Do the work. The ones that you'll have won't be overly difficult on the homework assignments. A couple of them are on the homework assignments that you're looking at problems for this week. The next assignment I give you, you're going to be looking at problems that are a little bit difficult, but just go through the step-by-step process in order to solve the problem. We're interested in the process. Given more time, we can all work through it and look at it several times and make all of our corrections and get it correct. Any questions today before we part ways? So if there are no questions, we're just going to continue to do a couple more examples, and then we're going to start to get into some pretty important concepts about the transfer function, why these functions are so important, how they're used, what is convolution, what really happens when an input goes into a system, what really happens, how does the world really see it? And what I mean by that is you take the input, you flip it over, and then you insert it into the system. That's really what happens. And we'll talk about why that happens and how we solve those problems, and that is convolution. So have a good day off tomorrow. I'll see you on Thursday. Stay safe, stay away from people, and continue to get that work done on the problems that you're working on right now to get a good jump and be prepared for our exam on Wednesday next week. I will see all of you on Thursday.